How can the Campi Flegrei caldera deform so much as it has done in the last decades without producing yet a new eruption? And when will the next eruption occur? These are pressing questions in a highly populated area. In the course, we have attributed sudden ground uplift to inflow of new magma into volcano roots, and mentioned that some gradual deformation may as well be due to viscoelastic response of the Earth to previous magma movements. But there is another possibility that one certainly has to take into consideration. Can changes in hydrothermal systems or geothermal areas cause ground deformation signals that look like signals due to magma inflow? This may indeed be the case, in particular in caldera settings that often have extensive geothermal areas. To explore that, one needs to look for changes in geothermal activity, like in one of the main geothermal areas of Campi Flegrei, the Solfatara field, shown in this video recorded by Halldór Geirsson. In a 2011 paper by Doria and colleagues, the interpretation was that the recent dynamics of Campi Flegrei was due to inflation in a deep part of the Campi Flegrei geothermal reservoir in response to mass and heat input from a magmatic source. When the pressure exceeds a threshold, fluid starts to migrate into the shallower part. During this transfer, long-period sources are activated in response to the fluid motion. The gradual diffusion of fluids in the surrounding rocks lowers the resistance of pervasive fracture system, generating shallow microseismicity. Finally, fluids reach the surface, which gives a distinct geochemical signature to the overlying fumaroles. This figure shows the hydrothermal system of the Campi Flegrei caldera and its signals according to a study by Giordini and colleagues. Panel A shows the locations of main hydrothermal sites, Solfatara and Picciarelli, within the Campi Flegrei caldera. Panel B shows a conceptual model of the hydrothermal system, a 4 km deep zone of magmatic gas accumulation that supplies fluids to a shallower part where they vaporize liquid of meteoric origin to form a 2 km deep vertical plume of gas. Panel C shows the temporal evolution of nitrogen-helium ratio at the Solfatara fumaroles. Panel D shows time series of the carbon monoxide concentration in the Solfatara fumaroles. The trends in the gas time series indicate heating of the system. The observations match well predictions from a numerical model, the magenta line, considering how gas ratios should vary in response to a temperature increase. The model fit is good. This figure shows the discharge temperature at the Picciarelli fumarole, gray dots, compared with the model temperature. The temperature increased from the boiling temperature of 95 degrees Celsius in 2005 to 2006 to 115 to 120 degrees Celsius in 2015. This was associated with localized low-magnitude seismic swarms, a weak phreatic activity in the form of mud emissions, opening of boiling pools and new vents, and a strong increase in the fumarole flow rate. The variation occurred concurrently with the increasing temperature of the hydrothermal system according to modeling. Here we see 3 panels for 2000 to 2016. Panel A shows average temperature obtained by a model for the central deeper zone of the computational domain. Panel B shows temperatures computed using the carbon monoxide and carbon dioxide geothermometer at the Solfatara fumaroles, compared with model temperatures shown in gray line. Panel C shows vertical displacement measured at the RITE GPS station as black line and modeled volume increase in the computational domain due to thermal expansion as magenta line. According to this model, the surface ground deformation can be explained as a result of temperature increase in a geothermal reservoir and the associated thermal expansion. the changes in temperature is how large, or about 60 degrees over the interval shown. But there is also a recent interpretation of geodetic and seismic data in terms of magma intrusion. This interpretation makes reference to a dynamic model for sill intrusion developed by Macedonio and colleagues who argue that the intrusion of a sill can be responsible for the dynamics observed during unrest at calderas. In their model, the sill is fed by a deeper magma reservoir, intruding below a horizontal elastic plate representing the overlying rocks. The sill expands with axisymmetric geometry. The model is based on the numerical solution of the equation for the elastic plate, coupled with equations for simulating the dynamics of a sill intrusion. The sketch of the geometry of the model is shown here, and also predicted time evolution of the sill profile, with profiles plotted every 3 months. This model predicts that after reaching maximum uplift above the sill, some subsidence occurs over the central part of the sill as its radius continues to expand. A paper by Doria and colleagues in 2015 uses this model to fit geodetic observations, with the resulting models shown here. The intervals begin on 1st of January 2012 and extend until the dates indicated: 25th August 2012, 26 November 2012, and 26 April 2013. The upper panels show a map view of the sill opening. Contour spacing is 5 cm. The sill center is in the center of the Campi Flegrei caldera at 3.1 km depth. The lower panels show the opening along profiles marked by the dashed lines. 2 approaches are used in this study. First, the sill opening is found by considering opening patches of volcanic dislocations. The results of that approach are shown here. Then, the opening distributions are compared to the dynamic sill model by Macedonio and colleagues shown previously. Good agreement is found between observations and models. Doria and colleagues conclude in a 2015 paper that they have the first evidence in the last 30 years of a renewed magmatic activity at Campi Flegrei caldera from January 2012 to June 2013. The ground deformation observed through satellite interferometry and GPS measurements are interpreted as the effect of an intrusion at 3.1 km depth of about 42 million cubic meters of magma. The interpretation is that this interrupts about 28 years of dominant hydrothermal activity and occurs in the context of an unrest phase which began in 2005 and within a more general ground uplift that goes on since 1950. In addition to the possibilities of magma accumulation and temperature change as explanation for certain features of the Campi Flegrei unrest, there is also the possibility of pressure changes in a geothermal reservoir for the same reasons that temperature change may occur, such as injection of volcanic gas into the reservoir. Indeed, all of these processes might contribute together. It remains a continuing challenge to separate the effects of each of these processes, limiting the possibilities to forecast the future behavior of the volcano and the next eruption in this otherwise peaceful part of the world. Therefore, good monitoring of the area is extremely important, considering the large signals of volcanic unrest.